Hello and welcome back. I'm Vivek and I'm creating videos on physics informed neural networks. So, in my last video, I spoke about how I used pins to crack a job interview. So, the job interview has many stages. I was talking about the technical interview and I have cleared that using pins. So, my attempt was successful. And we are still in this trial and error phase where we are trying to figure out what videos might be the best. We thought that doing a hands-on project-based video might be a great idea, and since this was fresh in my head, the pin code I'd written for this job interview, we thought that it might be a good idea to just go ahead and actually show everyone how that code works, how it was written, and sort of do a small hands-on project where you're actually tackling a real-world problem. And everyone learns differently, so we're hoping that this might be of benefit to a lot of people um, doing like a direct hands-on project. And the goal here was is that, let's say that you don't have all the information available to you and you're actually solving a real world problem, and there's limitations on how much time you have to solve the problem, what books you can access, and you need to get something done. There's a process to that. And let's say you want to solve a real world pin problem. How do you actually go about doing it within a certain time constraint? Uh, there's skill involved. There is like a certain amount of skill involved there, and that's what I want to show you. So, even though I'm a physicist and I like breaking everything down and deriving everything from scratch, and there's always an emphasis in my mind for like figuring out the truth, this might be more of an engineering flavored video where it's about getting shit done. It's about, you have a project, you have a timeline, and it's a real world project and you want to use pins and just get it done. And while doing that, you have to understand things in context and sort of learn things as you go and have this operational outcome oriented perspective. So that's the goal here. It's to walk you through actually the process I went through to write this code or code up this pin for this real world problem on such a short notice, doing a proof of concept. So I'll walk you through that process, and I'm hoping that you'll get an exposure to actually writing up like a hands-on pin code and doing a hands-on like pin project through this, and we'll sort of learn things as we go along. And the goal another goal of like our series is to have things hands-on and have things self-contained, meaning that you shouldn't have to look at the earlier lectures or sort of access other videos to understand this video or like this mini series. The idea is to sort of be able to understand it just using this mini series. So with that introduction, let's get started. So I have divided my code into smaller like code blocks or like Python files. So the actual pin, before we get to the actual pin, it's important to know where this pin might work. Like, you're usually given a data set, and the data set contains a lot of data, right? So data is king for machine learning, physics informed or not. It's, if you're thinking about any sort of machine learning, you want data. So given that you have a lot of data and given a problem statement, you still do need to understand the data to see how pins might fit into the big picture, and how you actually be able to use pins to like solve the problem at hand. And even if there's another question of feasibility, like is it even possible to use pins, or, and given a short time frame, what can you do, right? So you might look at the data and realize that you cannot really do pins, or you might realize that you can do pins but you can only demonstrate proof of concept on like a small sample of a certain kind. And that's what I discovered. But in order to do that, you do have to look at the data, and these conventional steps of data pre-processing, data segmentation, data loading, these are parts and parcel of like any machine learning pipelines, pin or not. So we will be going through that same pipeline where we have a data set, we sort of have to develop intuition for it. So there's the stage of data pre-processing. Once that's done, we want to use pin, but we'll realize that it's might be suitable to use pins on certain like portions of the data for a proof of concept. So you do need to segment your data in a meaningful way, and then we'll apply pin and sort of understand how it functions. And since we are using JAX, the plan is to use JAX. There is some JAX specific commands and code and ways of thinking that is like required, and there are some Python ideas as well, like object oriented programming and Lambda functions and decorators and accessing memory location of functions, just things like that, that I wouldn't want to directly have you like look at that code in the pin Jupyter notebook. It would be nice to sort of have like a Python crash course, like a Python goodies notebook before we actually jump into all of the code. And I did mention that we would want to have keep everything self-contained. So with that philosophy in mind, this will be a mini series where you have sort of 4 videos, and the mini series will be self-contained, even though each video might not, but we will strive to do it. So with the introduction out of the way, with sort of the mini series plan done, it's now time to actually open up the Python Goodies Jupyter notebook and walk through the cells step by step. One more thing that I want to mention is that I won't be helping you with installing JAX, or I don't know what other packages are being used. The typical ones like NumPy, Pandas. I won't be walking you through installation of the specific Python libraries or installation of Anaconda or Jupyter notebooks and navigating them. The expectation is that you know how to do that, and even if you don't, installing packages is very simple. You just need to first install Anaconda and then just pip install name of package in the Anaconda command prompt. And I know I'm just like telling this to you without demonstrating it. So the best way to get help for this is to just ask ChatGPT. Just tell ChatGPT that I need to install this and it will walk you through it. It is pretty trivial and it is common knowledge, which is why I'm not covering it here. Although I could have covered it, but my suggestion to you would be just go to ChatGPT and figure things out which I am not covering, which are pretty common. Okay, so in case you don't have things installed, just ask ChatGPT for help with installations, at least the Anaconda part, and even installing packages and upgrading them, and navigating and using Jupyter notebooks. You might even want to look at a few YouTube tutorials, like 5-minute YouTube tutorials. So those are, I guess, the small set of prereqs, that computational prereqs that we won't be covering, but I'm giving you tips as to how you would go about getting those aspects covered. So now that we have discussed like the very, very basic computational prereqs, we can now actually jump to opening up the first Jupyter notebook on Python goodies, like part 1 of this mini series. So great, we have this Jupyter notebook opened up here. So the first thing I'll do is just import the relevant libraries. This is very standard practice to just have whatever libraries you want imported right at the start. So we'll be using JAX, as I said, and we'll be using NumPy, but you can access NumPy through JAX by using jax.numpy. We'll also be using time, just because I want to demonstrate some very powerful features in JAX in relation to how fast it runs, and that's why we need the time package. So we usually press Shift Enter to run a cell in Jupyter notebooks. So I'll do that. Okay, so that's run. The next thing you want to talk about are Lambda functions. So what are Lambda functions? So I'm guessing you've heard of functions in Python. The way I understand functions is you want to do a certain procedure repeatedly. So you have a block of code which does that, and that's wrapped into a block called a function. Now, typically there's a certain syntax to write functions, and that extends beyond more than a line, because you need to define your function with a name in the first line with the argument it's supposed to take as input. Then you do the processing, and in Python you actually return or sort of output whatever variable you want, or whatever it is that you want. But there might be cases where the function is really simple and you might want to just write it up in one line, and there's a way to do it, and that's the lambda function, where it's a one line syntax to write up the function, but it doesn't have a name. So we'll first look at a very, very simple function which you would want to write up in one line, and we'll actually see that that function doesn't have a name. So let's just think about squaring a number, right? So you have just um, x into x. Now, since we, as I said, we want to use JAX and the numpy within JAX, we have imported the numpy within JAX as JNP. So if you have x, JNP dot square of x is going to square a quantity x, right? So the way you use lambda functions, the syntax is it's lambda arguments colon expressions. So your argument is x, your expression is the square of x, which we are using JAX's numpy to calculate. So your expression is jnp dot square of x. Your argument is x. So your syntax is going to be lambda of x colon jnp dot square of x. And we are saying sqfn is equal to. So in that sense, there is a name to this function, but it doesn't have a name in the Python sense. So I'll show you what that means. First, let's execute this line of command defining this function. So we did that. Now we'll execute sq underscore fn. So you see it says function double underscore main double underscore dot lambda. Now I'll get to the point where it doesn't have a name. We'll have to sort of compare it with a typical function with standard syntax used to compute this square, and we'll contrast it to see it doesn't have a name. So let's just first compute square of 3. It's 9, which is good. That's what we expect. Now we'll define this as a standard function. So I'm saying reg underscore sq underscore fn. Reg just means regular. I like to have very clean nomenclature for my functions. And then I'm going to take as argument x, and then I'm actually going to return jnp dot square of x. So I'm going to return the square computed using this jnp. So let's run this block. And now if I run reg underscore sq underscore fn, you see it says function double underscore main double underscore like dot reg underscore sq underscore fn of x, right? But if you compare it with the earlier function, it just said lambda. So, and here we have named it like diff reg underscore sq underscore fn. So you see the name appearing. So that's what we mean by lambda functions don't have a name, and that's why they are anonymous, and they are one-liners. So there's anonymous functions in Python which are written as one-liners. And let's just execute this regular sqfn of 3 just to see if it gives the same answer. It does give the same answer. So this is how someone would typically motivate lambda functions in Python. But as I said, I'm a physicist. I'm coming at things from a physics perspective, and we want to study pins. And one thing which is like bread and butter of this pin framework is differentiation, specifically automatic differentiation. So you want to differentiate functions in Python using JAX's capabilities. So what that means is, suppose you have f of x, you want to compute maybe f prime x, f double prime x. So in that case, let's say you had the function, but the function is a function of some independent variable or variables. So if you have f of x, right, x is your independent variable which is an input to that function, and you have a function f of x. Now you might want to calculate df dx, right, just the derivative f with respect to x. Now if you define your function using lambda functions have the form lambda argument colon expressions. So you can have an argument x and your expression is f of x. So this sort of way of defining functions using a lambda function tells you in one line of code what is the input of the independent variable, what is the function. So if you want to differentiate things, if you just provide the lambda function lambda f x colon f of x to the automatic differentiation engine, it automatically knows, oh, I need to differentiate f with respect to x. That is why it comes in so handy, and we'll be looking at that sort of use case later on, this way of using lambda functions in context of automatic differentiation for physics problems in PIN. So I hope that motivates the lambda function. And as I said, we'll be interested in looking at where our functions live in the memory space, like where are they located, because there are going to be some subtle points coming up with respect to memory locations when we actually get to the pin code. So this is very simple. You just say id and parenthesis, you just put the function. So if you look at id sq underscore fn, that's where a lambda function lives. You get this big number. If you put like reg underscore sq underscore fn in this id thing, you get a different number, which tells you both these functions live in different locations in the memory like hub. So that's important. We've defined two different functions. They occupy different spaces in the memory. They have these memory addresses. So that's good. And we'll be using this later on. The next concept I want to talk about are list comprehensions. So let's say you actually want to create this data structure called a list in Python, right? And let's say you're doing some sort of iterative operation. Like let's just think about the square. Let's think about squaring the first four natural whole numbers. The first five whole numbers. So 0, 1, 2, 3, 4. Right? If you square all of them, you might want to square all of them and just put them in a list. Now, one nice way of a standard way of doing it is you just have a for loop. For loop is an iterator and it's going from 0 to 5. And you just square every number and you append it, you sort of put it, stick it in a list, in an empty list, right? But the same thing can be done using one line of code, which incorporates a for loop. So you're creating a list, but you have this comprehensive, nice, compact syntax to do it. And that's called a list comprehension. So let's sort of do a quick example sticking to our squared numbers, very basic use case. Let's sort of square numbers from 0 to 4. But let's first use a list comprehension and then let's use a standard for loop. So when you use a list comprehension, you have these brackets on the outside. That's holding like the contents of the list. And then what do you want to do? You want to get squares of numbers, right? So, and we are using like JAX's numpy square. So we do jnp.square of x. But then you say for x in range 5. So I'm saying that my x is going to go from 0 to 4, right? Using a for loop. And for every element in that iterator, I want to do the square. So it's sort of, here you have like expression on current iterate, and then iterator expression, which is the for loop, inside like the square brackets. That's the syntax for like list comprehension. So let's go ahead and run this. So it's like y underscore lc. lc is for list comprehension. I like to keep my name cleans. So y underscore lc is square brackets jnp.square of x for x in range 5. So we'll run this, and you see it's array 0, 1, 4, 9, 16, which is great. We are getting arrays returned because we are using JAX's numpy, and it returns arrays when you do mathematical operations, which will again come in handy later on to have clear data structures. Now we can do the typical thing where you define an empty list, you loop through 0 to 5 using a for loop, and then you say for x in range 5 colon, and then what are you going to do at every iteration? You're going to square x, so jnp.square of x, and you're going to append that to your y underscore reg list, reg for regular. So we'll go ahead and do that, and you see we again get like the same answer. This just contrasts both methods, but list comprehensions provide nice compact syntax with a for loop to do the same thing that you would do with a for loop. And this comes in very handy, and we'll be looking at this later on. So this is the basic idea of a list comprehension. So now let's move to the next idea, which is the enumerate operation. So this again has to do with iterating through um, iterators and like using like for loops. So let's say now we have and let's also build on top of examples we have. So now we have this example where we have a list of squares of numbers, right? And let's say you are interested in actually accessing the index or the location of these elements in the list. So you have a list, they have squares of these numbers, but you want to access where they're at, and where they're at is actually what you've squared. So you might be interested in like looking at the number, twice the number, and the square of the number. And the index or the location in the list of your square, that actually is going to give you the number which was squared. So you want to, that's why you're interested in accessing the index, and then you want to double it. So now let's say you want to simultaneously iterate through a list, not just accessing the list element, but its index. You can do this using the enumerate command. And the syntax for this is so you say index, which is the index of the current iterate, comma, like the actual iterator, the the iterate in the list, in enumerate list colon, and then you just do whatever you have to. So here we say for idx comma item in enumerate ylc colon, and then we are saying print idx 2 times idx and the item. So we're iterating through the list using enumerate. Item is the actual square, idx is the index or the square root of that number, 2 times that is twice that number, and item is square. So let's see if this actually works. So it does work. So you see that the first column is just all the numbers 0 to 4. Then you have double the numbers and then the squares. So that's how you can access the index while looping through using the enumerate operation. And this will come in handy just when you write a lot of Python code. So something to bear in mind. The next thing we want to look at is zip operations or zip objects. So what is this zip thing? So let's say you have 2 lists and you want to iterate through them simultaneously for some reason. So let's say here I've created an example where you have 2 lists. The first has the numbers 1, 2, 3. The second has the numbers 99, 98, 97. Now if you note, they always sum up to 100. So maybe you're like, oh, you want to like loop through both these lists simultaneously and see if the corresponding elements, or by corresponding I mean at the same index, if those two numbers sum up to 100. You might be interested in that. So then you would have to iterate simultaneously through both these lists and sum up the item at that index. So what you do is you zip these objects together, right? You say zip zip parenthesis list 1 comma list 2. Now this creates something called a zip object. So let's just run the code and see what happens. So we'll do this. See, type of zip object is zip. So it creates this entity called zip. Now if we do zip object, you said zip at this, at whatever memory location. So this is an iterator, meaning you can iterate through it, and you can loop through it. And what it stores, it is a collection. When we say we're going to iterate through it, you're iterating or looping through a collection of items, and each item is a tuple. Okay, so here what we'll do is we'll say for tuple object in zip object, right? So you're iterating, looping through this collection of items, which is in the zip object. Every item is a tuple, and we're interested in the 2 numbers residing in that tuple. So we have num1 comma num2. So parenthesis num1 comma num2 just means I have a tuple with the first entry num1, second entry num2. We are saying that equal to tuple object. But tuple object is a tuple with 2 numbers. Num1, so the first number will get assigned to num1, the second number will get assigned to num2. Then let's print num1, num2 and num1 plus num2 to see if the sum is actually 100. And if this works, that will sort of give you a sense of iterating simultaneously through 2 lists by zipping them together, extracting the tuple object, and then doing operations on the tuple. You see that it's printing 19900, 29800, 39700. So It is iterating through a collection of items where every item is a tuple. We are then extracting the two numbers making up the tuple. We are printing them and printing their sum. So this is how you would use zip objects, and we'll be using this later on. Another idea to have at the back of your mind while writing code in Python. Okay, the next concept that we want to talk about are called decorators, and this is more specific, or I would like to discuss this in the specific context of just-in-time or JIT compilers in JAX. So JIT compilers are what is like one key feature which makes JAX so powerful, because it will make things run super fast. And to access that power, you need to understand the idea of decorators. Now, although in the actual code is just one line which accesses the JIT compiler, but having an understanding of what's going on under the hood, at least at a basic conceptual level of what you're doing, will sort of just help you write your pin code and sort of know, okay, this is what this means, this is what the syntax means. So the way JIT compilers are accessed are using decorators. So what are decorators? Decorators can be thought of as something which enhances the capability or extends the capability of functions. So let's take a very simple example. Let's start with the first example anyone encounters when they're learning Python, and that is the example of printing the hello world statement. But let's do that using a function. So here we are defining a function saying print hello world, and inside that function you just print hello world. And by the way, because this is a function always returns something, and since we haven't said anything about the return, it will return none. Just something which came up in my head, so I told you about it. But anyways, now let's say we want to extend this functionality or expand on this function so that it prints more than just what's given in your function block. So let's say we define another function, print hi world. And in this case, we want to print more than hi world. We might want to say something is happening before this function is called, then print hi world, something is happening after this function is called. So you want to extend this functionality. So one way of doing it is, well, let's say you had another function which did do this. Like, let's say you had another function which could take in this hi world function, print something before this function is called, then execute this function which will print hi world, and then print something this like happening after the function is called. If you had something like this, that would be great. And if you had syntax where you could actually do this repeatedly, that would be great. There is a way to do it. Suppose there's a certain enhancement you want, and that can be done using this function called decorator. You say at and the name of like your actual decorator function. In this case, we have named the decorator, but in pins it'll be something like at eqx underscore JIT compiler or something. So here, if you say at decorator def print hi world, and then you have the syntax. So when you say at decorator, it means that whatever is inside your new function, that's going to be passed to this function enhancing decorator function, and it'll do whatever enhancement it has to do, right? But what enhancements do we want here? We want just a print statement before the function and after the function. So let's first actually look at the decorator function. Let's just run it. So this decorator function will take as input a function. Inside that, there'll be something called a wrapper function. And in this wrapper function, what we're doing is we're saying print something is happening before the function is called. So it'll print this. Then it'll actually run the the actual function which is being input to this decorator function. Then it'll print something is happening after the function is called, and we say return like the wrapper function. So this is the standard syntax to create a decorator function. So let's just run this. Then we'll just define a print hello world function. Now for our print hi world, we are going to say at the decorator function. In this case, the name of the decorator function is decorator, and then the syntax for your function, which is def function name print hi world no input, so just the empty parenthesis colon and then the actual function body, which is print hi world. Let's run this. Then we'll run print hello world. It just prints hello world. Then we'll run print hi world. Now it prints something is happening before this function is called. Hi world, something is happening after the function is called. So you see that the hi world, print hi world function, its capabilities were enhanced with this decorator function, right? This decorator function ensured that something was being printed before and after this function was called. So this function call was executed, hi world was printed, but before and after that things were printed, and it was enhanced by calling this decorator. And our current hi world function is being passed through a decorator. And the syntax is extremely simple. It's at decorator function, actual code to create your function. So in our JIT compiler, what happens is you want code to run very fast, especially the step where the optimization happens in the pin. So the actual function where the optimization happens, you'll actually have a function saying define make optimization step with your Adam optimizers and whatnot on the loss function. Now if you just run it, it will run really slow. But if you just put a at JIT compiler on top, it just runs super fast. And that's the power of JAX, which we will experience later on. But this all boils down to using a concept called the decorator. And because this is related in some ways to interviews, I can tell you this, that if you actually take any live interview, you might have lead code style questions. Some do these assessments where there's a timer running and there are very short questions with options. You might face a question about decorators, because those assessments will categorize you as intermediate, advanced, or beginner. So for the advanced questions, there will always be one question on decorators. So something to keep in mind from the perspective of cracking coding assignments, live coding assignments, nothing to do with physics, but just something to keep in mind about interviews. So now that we have talked about decorators, we talk about a simpler concept which is very prevalent in Python and NumPy and Pandas coding, which is slicing arrays. And array slicing literally means cutting or slicing an array. And the syntax simply is you have a list, bunch of numbers or a collection of items. So you want to maybe slice, right? In your mind, think about like a red colored block, and inside that block, you want a small block, blue colored block, right? So you just have to know sort of where the start and ends of the block are, and then you just cut it up. So the syntax is really like your array, uh, square brackets, start index, colon, end index. And in this case, when you say start index, that is included. When you say end index, that item at the end index is not included. Another thing is, if you don't put anything at the start, it'll start right from your first thing. So there's no slicing or cutting at the left end. And if you use a minus one typically refers to the last element. So if you put a colon and then a minus one, it means include everything but the minus one, so it will not consider the last element. So let's look at very simple examples. So I just have an array which has numbers 1, 2, 3, 4, 5. Right? We'll just run this. Now if I say up to 3, right, and on the left I'm not saying anything, it means it won't do any cutting or slicing at the left end, but it will go up to the index 3 and not include the index 3. So in our case, index, we start from index 0, then index 1, index 2, index 3. So it is not going to include the element at index 3, which is 4. So I think it should just print 1, 2, 3. Let's see if that works. Yes, it prints 1, 2, 3. Now the next example is, on the left we have 2 and the right we have 4. This means it will include the item at index 2 and exclude the item at index 4, and we'll have everything in between. So we have 1 at index 0, we have 2 at index 1, we have 3 at index 2, means 3 will be included, and then we have 4 at index 3, 5 at index 4. 5 will not be included, means 3 and 4 should be printed. Let's check that out. Yes, it works. Now array example, nothing on the left, colon till -1. -1 means exclude the last element. So what should be printed is 1, 2, 3, 4. Great, that is printed. So array slicing, very simple ideas, and we have covered those. The next thing we want to talk about are type hints. So type hints are typically used for improving code readability and for having very clear code. It's good practice. It is telling, like, one thing about code is not written for machines. Code is actually written for humans, right? Because like when you write code is executed at like the machine level, which just understands 0 and 1s. So what language you use, how you write it is completely it doesn't really matter to the machine. It matters to you because you have to debug your code. You will have to write complicated blocks of code, and you will probably share your code with other developers, other people, right? So that's why it's important for humans to write clear, readable code. It's not for the machines, it's for you. And one way of doing that is through type hints, meaning you clearly specify what the expected type for a certain variable is. And in Python, type hints are not strictly enforced, meaning that even if you specify it, if it's violated, it doesn't matter unless you put, I forgot what it was called, I think. Yeah, but anyways, it doesn't really matter. It improves readability, right? Yeah, unless you put a try except clause. That's what I wanted to say. So here we just want to add two integers, right? So we can have a function def add two integers. That's the function name. It's going to take in two arguments, first num and second num. And we want both of them to be integers because we're adding integers and we want it to return an int. So first num colon int, second num colon int, and then that arrow and int means inputs are integers, output is an integer, and then we'll say return first num plus second num. So we'll run the function, run the code on 1, 2, it'll return 3. Then we can run it on 1.1 and 2.2, it returns 3.3, right? But the thing is, as you see, if the type int was strictly enforced, it shouldn't have been able to, it should have thrown an error, which it did not for 1.1 and 2.2. The reason being it is not strictly enforced. But the clear naming of the function and providing type hints tells the user that I would like to add two integers. It makes it very clear. So that is the reason we use it. I hope this example has given you some insight into type hints. The next thing we want to talk about is very different from type hints, very different from what we've been talking about till now, but it's the idea of random keys in JAX. So in JAX, when you set up neural networks, we spoke earlier in like the big introductory video that we can think of neural networks as mathematical abstractions of intelligence through which information flows. And the way this information flows is you have these layers, and these layers contain these units called neurons. And as information flows, the network learns, in the sense that some information flows, you have information with which it can compare what it thinks, and if it's done a bad job, it'll sort of realize that, oh, I need to sort of do something different. It'll learn from its mistakes and new information will flow. But it starts somewhere, right? It starts at some state. It starts with some preconceived notion of trying to make sense of what information is given to actually make predictions or build a mathematical model to gain insight. Just like the way your human brain starts with some baseline idea. That baseline idea, the word for it is initialization. So you need to initialize neural networks so they have an initial state. And when to create an initial state, you want to create a reproducible initial state which doesn't always change, right? Otherwise you every time you run your code, you'll get a different result. It will be hard to sort of trace back what's really happening and understand what's happening. You want to have it in a way that it's reproducible and you can run the same code every time, which means its starting point must also be the same. And when you think about neural networks, the way it's initialized, just think about the way you think. You don't always have a clear-cut, well-formed idea right at the start. There is some randomness to your thinking. The same way, there are some random numbers involved when you initialize this initial information paradigm in a neural network. And that is how random numbers come in. But random numbers are random, right? So we don't want it to think about completely random states every single time. Otherwise, there's no way to track back to a fixed initial state and know what's happening. So we want it to be pseudo random, where it's a bunch of random things it comes up with, but it's the same set of random ideas it's starting out with. So when you think about the way you think, you might, like, let's say there are like 10 different people who are trying to learn an idea. So every time similar ideas are given to the first person, they might start with sort of the same kind of random thought process, and they iterate and they learn. Someone different might start with a different random thought process, they iterate and learn. But one person given 10 different ideas, similar ideas, they always seem to start with one kind of random, very similar baseline thinking, right? It reflects their thinking pattern. In the same way, we want a neural network to sort of always start with that same random thinking pattern. It's pseudo random. And JAX doesn't explicitly tell you how it's doing the initialization, but it does use random numbers, and we want these random numbers to be at some level fixed at every initialization. So in a way, they're pseudo random numbers. So the way it is done is in JAX, you generate something called a key, a random key. And once you generate that key is actually used to initialize this information paradigm in a neural network. And you might have to initialize different blocks in the neural network, meaning that you need more than one key. And that key might have to be cycled and tweaked to initialize things at a later stage or in different sequential blocks. So there might be more than one key, and these keys might talk to each other, and you might be recycling and improving keys and storing them in these fixed 2-3 key variables. So typically you need to initialize a key and you need to split a key. These two operations will come in very handy. And these are, as we have connected them to random numbers, right? There is this idea about randomness, and we are using random numbers. That's where the random part comes in. So the syntax to do it, to initialize a key is equal to jax.random dot prng key, and you just put in a number, a seed. It's called a seed. So we put 0 here. So we'll initialize this and we'll split it to create a new key, right? So you'll have your key that's split. So your key turns into something different, but you also get a different key out of it. And we'll sort of be using these patterns and see how this plays when we actually code up our neural networks. You'll sort of see how various blocks are initialized, how things change when you iterate, and how these blocks talk to each other, and why you need keys initialized this way and how they talk to each other. So this random.prng key with a key seed 0 and splitting keys will be very important. So now we'll say key underscore new key is jax.random.split key. Great, this is run. Okay. So moving on to the next important, really important concept, and something very fascinating about JAX, which gives JAX so much power, is called the vectorized mapping or VMAX feature in JAX. And what is this feature? So let's think about functions, right? So let's say that you had a function where you had a vector, and a vector has, let's say it's a 2D vector. So it has two entries. Like in physics, you can think about a position vector in 2D. And you want to know, like, think about displacement and distance, right? You're walking somewhere from a starting point. You want to know how far you've moved. The distance gives you that. The displacement is the vector describing your position, or the position vector. So the norm of this vector tells you where you're at. And you can also think of the norm comes from square rooting the squares added of the two components, right? So now think of a function to do this. You'll take the vector, you look at its two components, you'll square each and you'll add them up. And now let's say that I don't have one position vector, but I have data consisting of like a lot of position vectors, and I'm interested in evaluating the norm. Or let's say I have a bunch of displacement vectors and I'm interested in computing like the distance for each, right? Now I can write a function which does that, and then I can run it for each of this vector in this collection of vectors, right? Now that operation is called vectorization, and you can do it using a for loop, but it will definitely be very, very costly, or using a list comprehension, but it will be costly. Now, if you think of this operation which I had just described, the beauty about NumPy or JAX NumPy is that there are ready-made out-of-the-box functions to do this. So you'll typically use these functions and you'll do it. And by doing it, it will sort of auto-vectorize the code. But you might be in situations where you have custom functions which are not trivial to vectorize. And in that case, then when you do the list comprehension of for loop, it is painful. If you had something which could vectorize these functions and ensure that something operating on an item or one element can be vectorized to a batch of such items or elements or vectors, that would, in a way that enhances computational speed or reduces the burden like vectorization with a loop would have caused, that would give you a lot of power in computation, and that's exactly what VMAP does. Another reason why it might be required is you can think of conceptually where you want to think about, like mathematically and in physics, about just you want to think about functions, right? Mathematical functions acting on a scalar or a vector. You want to think, let's say you think about physical fields. So let's say you're interested in the velocity vector field, and you have a particle moving in space, and you define its movement or describe its movement using its position vector, right? And the position vector might change with respect to time. Now the velocity vector is defined as the first derivative of the position vector with respect to time. It's drdt. So conceptually, when you think about this, you're interested in differentiating a function with respect to time. But actually in computation, you might have a particle moving in time, right? A particle may be doing projectile motion for 2 seconds. And you might have the actual data about the position vectors, maybe the x and the y, for 2 seconds. And you might be interested in computing the velocity vector at each time instant. But conceptually, what are you doing? Conceptually, you need to compute the derivative of the position vector at a given time. That gives you the velocity vector. And then you're interested in evaluating this velocity vector for the entire array of these position vectors. You want to sort of vectorize this or sort of extend this operation to a batch of position vectors spread out through time. And that's another thing, another place where vectorization comes in so handy from a physics perspective. So we'll sort of be even seeing this from a neural networks perspective and vectorizing a neural network later on. But these are some ideas as to why you need vectorization and how JAX's VMAP comes in really handy for custom vectorizations in case the functions are hard to vectorize. Another use case we'll see later on when we deal with very specific forms of characterizing orientations. And the other thing is when you're conceptually thinking about functions and you're thinking about functions evaluated at a given time instant or acting on vectors or scalars, and then you want to extend that operation to a batch. That's another place where vectorization comes in very handy. So now let's actually walk through this example of, we won't compute the norm of actually we will compute the norm of a vector, but we'll define it differently where we don't bother about taking the square root just because it doesn't matter for the illustrative purposes here. The first thing we do is define this vecnorm function. It takes as input vec, a vector, and we haven't used type hints, but we'll just, for now it doesn't matter, but you should use type hints. X is the first component of the vector, so vec of 0. Y is the second component, so vec of 1. n is this squared norm. So you do jnp dot square of x. We are using our square thing again. Comes in handy. We have discussed a lot of examples with square. It's nice that it's here as well. So you do jnp dot square of x, jnp dot square of y, add it up, assign it to n, return n. So let's just run this function. Now let's actually think of you have a angular variable theta, and it goes from 0 to pi, and it's a discretized collection of angles, but I'm ensuring that we have 100,000 discrete points, and the reason I'm creating so many points is to show you how things will slow down later on when you don't have this vectorization functionality. So now let's think about like points in a circle, right? 0 to pi. And let's think about the position vector going out to that circular arc and the x and the y component. So x is just going to be like the cosine. So jnp dot cosine of theta, it's a unit circle. Y is going to be jnp dot sine of theta. And then I want to store all of this information in an array, right? So let's say I had two column vectors, one with the x components, one with the y. You would want to concatenate them. You want to, in the columns direction, you want these two columns and then a third column with the displacement. So the first thing I do is I'm going to do jnp dot cosine of theta, and theta is not like a column vector, it's just a vector containing a bunch of elements. So I need to reshape it to a column vector, and while reshaping it I'll put 1 at the very end. That's the column index. I'm saying I want to reshape it to one column. -1 means don't care about anything before it, ensure that I get a column vector. I'll do the same with y, and then I'm going to concatenate them using jnp dot concatenate x comma y. Axis is 1 means get a third column, concatenate along this direction, which is going to be a vector with like x comma y, x comma y. So let's do this. So we have this. Now we're going to use list comprehensions, and what we're going to do is we're going to say first we're going to record the start time. So we're going to say that before I start this computation, what's my Python clock? Where is it at? Then I'm going to compute the vec norm for a vector for every vector in this list, this array vex, right? And I could have said for vec in vex colon and then done it, but we are going to use list comprehension. So we're going to say expression and then your for loop and everything in the square bracket. So we're going to do this. And we're going to then note the end time, and then we're going to look at the time in between by taking a difference, the execution time, and underscore reg just means the regular way of doing it. So let's do this, and this will actually take about a good minute to run. Yeah, it does take a long time to run. Now you have this where we record the start time. Then we say JAX.VMAP of vec norm. Vec norm is the function. JAX.VMAP means vectorizes function. So JAX.VMAP of vec norm is the vectorized form of the function, and then we are going to apply it to vex. So you have the parenthesis and you put vex. We'll record the end time and we'll note the execution time. Now I'm going to play this. This is going to be a real surprise. Look at that. And now let's print the times. So execution time, regular 35.15 seconds. VMAP 0.18 seconds. Like that is just insane, right? It's like orders of magnitude faster. So that's the power of VMAP, and I hope I've illustrated why we need it and motivated it from a physics perspective, and that's a really strong feature of JAX. So we'll be using this later on. Now let's build on this. So I was talking about position vectors and velocity vectors and automatic differentiation, and then I said that we want to sort of like using VMAP. When you have a function, you take a derivative and extend that concept across a bunch of collection of position vectors. That will come in handy. So let's actually do an example. Let's bring all the ingredients together. Like that's sort of all the ingredients are going to start coming together now that we're almost reaching the end of this tutorial. So we spoke about Lambda functions and using them to because of their syntax, because it will be good for automatic differentiation. We spoke about using squares and we spoke about automatic vectorization or VMAP. So all of these concepts are now going to come together in this example. So now let's think of projectile motion, right? And in projectile motion, we want to think about the first 2 seconds of projectile motion. I've scaled things, so I've scaled gravity. It's like I'm not using the exact numbers, but think about a 2D projectile motion in a 2D plane, and you're starting from the origin. So projectile motion is characterized by like one component of the position vector which goes as a square of time, right? You have square dependence. So let's say that your first, like it's 2D projectile motion. So let's say your first component is just t. So in that direction you have like constant velocity vector which is like 1 unit. So it's just going at t, and in the other direction you have some acceleration, and that's why let's say you have t squared. So now let's say your position vector at every time is characterized by t squared, and you actually want to compute the velocity vector for this movement for the first 2 seconds. And let's say you have a discrete time array sampled uniformly 10 times throughout these 2 seconds. So the first thing we would want is to compute the derivative, right? We need, like, it'll be nice to have some sort of automatic method to do it. That's where automatic differentiation comes in. And this JAX.JACREV command is like the powerhouse of this automatic differentiation. So now, how does it differentiate? It actually requires a function where you sort of supply the function and you supply the independent variable. So now if you supply a thing like lambda argument expression or lambda x f of x, or in this case lambda t colon position vector, it will know that, oh, I have to differentiate with respect to time and my function is a position vector. So it will know it's supposed to differentiate the position vector with respect to time. You see how convenient this lambda function is for specifying the syntax for this automatic differentiation. And what does JACREV mean? So JAC stands for Jacobian. Jacobian is required when you want to differentiate a vector valued function. A position vector is not a scalar, but it's a vector. It has an x component and a y component. So, or it has a first and a second component. This movement in 2D. So that JAC means differentiate a vector valued function, and JAC is Jacobian. REV stands for reverse mode automatic differentiation. So you can do forward mode automatic differentiation or reverse mode automatic differentiation. Both give you accurate answers, and reverse mode is typically used when the number of inputs to your function is really large. We are interested in later on replacing quantities of interest with a neural network which takes as input something called weight and bias parameters, which are really large compared to maybe one output which is a scalar or a vector of physical quantities with just 3-4 entries. So, but in our case, even if we characterize things with a neural network, the weights and biases are not active parameters because they're like hidden parameters, and we might be interested in differentiating with respect to like maybe one variable, like a physical variable like time. So reverse mode is typically used when you have a lot of input variables. So in our case, we have a lot of input variables, but the active input variables are only one. So that argument might not hold. So it might be hard to justify why we are using reverse mode differentiation for PIN or for this given our specific use case. It's not very obvious why we can't use forward mode, but both of them give accurate answers, and JACREV is very, very commonly used. So there's no loss in using it. So I would say that from an operational perspective, so like I said, I was sort of did this when I was solving an assignment. Both give you accurate answers. And it doesn't really matter, like the accuracy matter, the speed is similar, and it doesn't really matter, so you can use JACREV. So that is the motivation. The important part is Jacobian, because we are differentiating a vector valued function. So we say dr underscore dt, again keeping names nice, because we want a velocity vector where it is derivative of position vector. So that is why I've used the name the variable dr underscore dt. Is JAX or JACREV. So we are going to compute the Jacobian, which is the derivative of vector valued function using reverse mode automatic differentiation. And our function is specified as a lambda function, which is argument expression. Your argument is time, your expression is the position vector, which for a projectile motion is t and t square. And for t square, we're using jnp dot square of t. Let's run this. Let's run our t val. So that's just a time array. Let's look at t val of 0. So that's 0, right? Now, let's actually compute the velocity vector at t is equal to 0. And the answer should just be like 1 comma 0, right? Because position vector is t square. If you differentiate that, you should get 1 comma 2t. At t is equal to 0, you should get 1 comma 0. Yeah, so you get 1 comma 0, which is great. But now this has been sort of defined for one item, one vector, and we need to vectorize it so it can be applied to an array of times, right? That's why we need to vectorize this. So that's where the VMAP comes in, which I had explained earlier on. So we'll say JAX.VMAP of drdt, that's drdt vec. That's the vectorized version. Let's run this. And now let's run this on tval. We run this and it prints out the collection of velocity vectors. You see the first one is 1, 0. So our velocity vector, the first component should always be 1 because the derivative of t with respect to t is 1 and the derivative of t square is 2t. So the second column should be start from 0 and go till 2 into 2, which is the final time, which is 4. And you see that is actually happening. So this actually works. So this is an example where we actually used lambda function, the jnp dot square. We have actually used a vectorized mapping and we have used automatic differentiation. So all of the elements we spoke about have come together for a physics example. And now it's time for the final concept we want to cover, which is slightly heavy and it's not typically taught, I guess, in physics courses, but it's something we will really need when we code up the pin, and that's object-oriented programming, and we'll talk about the basics here. So the idea here is let's actually stick to our projectile motion example. So in our projectile motion example, what we're interested in doing is characterizing the movement, describing the position and the velocity vector as it traverses through time. Now, as a physicist, the way I would think about this is, let's say someone said, describe the movement. How would I go about this? I would actually want the differential equation. I would think about the complete movement. I would use a reductionist approach where I actually segment this movement into very, very small steps and think about what's happening at this in a small time step. Right? So you can think about it as propagating the particle or just the mechanics which is happening for a differential equation in a very small interval of time. That's the basic idea of calculus. And then I'll sort of apply that calculus right from the start, right? Play that movie and do that at every discrete time instant. So now, when I do this in the computer, I want some sort of nice container, right? I want some nice container which can hold, let's say it holds my position, it holds my velocity, and it knows for how long, for a small instant of time. Let's think about a small instant of time, right? It might want the position and velocity. You might want to know for how long or what is the duration of that small instant of time. And then you might need the physical law, meaning position plus velocity into time for both components, velocity into small differential time, right? That's like moving or propagating the particle. So so in the computer, you might actually want something to hold this information and do this operation, right? So the way we think about this is we first abstractly, right? Even when you think about this as a physicist, you first think about the set of instructions you want. You think about the variables, the information required to describe the physical system. So the first thing you need to do is characterize the physical system using appropriate variables. And then once you characterize that, you need to hold those variables in some containers, and then you need to think about an initial condition, and then you might want to carry out some operation repeatedly or apply a function. So you actually need a blueprint. When you think about all of this, when you think about the algorithm, you need a blueprint, which is a blueprint for a container, right? Which is reproducible, it's interpretable, right? And that container, right? If you have a container, in that container, you might want to assign specific properties, physical quantities to describe your system. So in object-oriented programming, specifically from a physics context, this is done using classes. So when we think about a class is a blueprint that to create, like reproducibly create understandable, like easy to interpret data structures. It's a blueprint, it's a set of instructions, and it tells you, oh, I need these variables to define the system, and these variables which define or characterize the system, these are properties, and these are called attributes, and you actually have to assign these attributes to something in that class in your blueprint. So this something is called self, and you always have an initial condition in physics or in computer programming. So to create an initial condition, you have something called a constructor, and a constructor is a method. Method is a fancy word for a function, and in object-oriented programming, it's done using the init method. So you say def underscore init, and then you say self, and whatever input you want to take in. And self is that, like, it's an instance of this class, right? Or in this blueprint, you are actually like creating these instructions. You want to assign properties to an instance. So these properties are called attributes. They're assigned to an instance using this keyword called self. It's done through this method called a constructor defined by init, right? And then you actually do a method or a function to actually do what thing you want. So these are the technical terms involved. But let's actually sort of walk through an example operationally, stepping through time, right? So think about this projectile motion example. So we're going to break it down. We're going to think about a small time step, and then we're just going to repeatedly apply that calculus. So what I'm going to need? I'm going to need a container, right, for time step. So I say class time step. That just means, okay, I'm going to think about propagating a particle, or how a particle moves in a small instant dt. I'm thinking about the calculus. So I need a container to like describe that. Let's call that time step. Now what am I going to need? I'm going to need position, I'm going to need velocity, and that small duration. And that small duration might be fixed, but every time we take a different particle, you'll have a different position and velocity. So then I'm going to need the properties or attributes defining my time step class are going to be position and velocity. And I need to initialize this. So then I say def double underscore init double underscore self comma position comma velocity. So this is just a function, and that function takes in position and velocity, right, which you give it, and then it's going to assign it to an instance of this class. So that's done using self dot position is equal to position, self dot velocity is equal to velocity, and then you say self dot dt 0.01. That's just a small time instant. Okay, so that's a blueprint to sort of create a container which takes in position and velocity and initializes it. But then you need to propagate that, right? You need to move the particle. That will be done using the physical law. So you need a function. Let's say def move. That move just takes as argument self, because you're going to actually propagate that particle which is characterized by self. And then you say what is the new x? It's just the position, the first component, which is accessed by self dot position. So you want to access position, you say self dot that attribute. So you say self dot position of 0 plus what's the x component of velocity? Again, you have to access it using self. So you say self dot velocity of 0 into the small time instant, which is dt. Again, accessed using self. So you say into self dot dt. What about the y? Same. You say new y is equal to now position access to self dot position of 1 plus again velocity y component access to cell dot velocity, the first component, cell dot velocity of 1 into, again, what is the time? That's dt, but access to self dot dt. So into self dot dt. And now your new position is new x comma new y, that tuple. And that is stored in position, but to store the position, which is the attribute, it has to be given to self. So again, we say self dot position is this tuple new x comma new y. Okay. And now let's say you want to do this repeatedly. So let's say you create this time step, right? When you create an actual particle which is going to step through time, that's called an object. That's called initializing an object. So let's say you did that. The next time you actually want to access that object, you might want to just move it forward. So the way to do it is you have this command, or you have this syntax called def underscore underscore call underscore underscore self. What this means is that, suppose when we'll see later on, we actually create this class. You create it by a certain syntax, but by saying time step and parenthesis. But the next time you call time step, it will actually execute the code inside call, which means it will execute move. So the way you think about this is you have a class which is a blueprint for creating reproducible and interpretable data structures for your problem. Then you create a class, and like example, that's called an object, and then you call that for some functionality like propagating it forward, in this case. So that you will do using the call keyword. So again, init is a constructor, initializes it, gives from some property, and you have to, whatever properties you want, just give them to self, right? And the next time you create an object, you want to actually sort of do something to it, you use call, and call will do whatever is inside that block. Okay, so this is what time step does. But as we said, we're using the reductionist approach. We are breaking down a big problem into small parts. So we have understood, or we have discussed what will happen in a small time dt. But now you want to repeat this process, right, from 0 to 2 seconds. In every dt, what you need to do is you want a time step. So you basically want to access everything in that blueprint for time step, everything in the class for time step. So we use a concept called parent class and child class. What this means is you have a child class, and the syntax is, let's say, class motion. So motion is going to be this class which tells us how to move this particles from 0 to 2 seconds. So we say class, child class, which is motion, in parentheses parent class, which is time step. So what is happening is everything in the time step class, the parent class, is accessible to the motion class. Meaning we want to step through time given position and velocity in a small dt. We can have access to all of that if we just put time step in the parentheses. And why is this required for pins and physics and stuff? This is a physics example, but in pin, we'll set up a neural network, and we don't want to do all the hard work, or we don't want to recreate the blueprint required for creating a neural network. That's already done in the JAX library. We need to access those modules. So we'll sort of be using equinox.nn.module as the parent class. Will be inheriting from that to use whatever is already there and extend its functionality. So in the same case style here, we say class motion of time step. It's going to take in time step, and it will have access to everything inside time step. Now in motion, again we need initial position velocity, but so then we need the def init. We say self comma, what are the attributes, position and velocity, so we give that. But now we don't need to do self dot position is position and self dot velocity is velocity and self dot dt 0.01. That's already done in a time step class. So we can use this command called super. So you say super dot underscore init underscore position velocity. That means take these arguments, and the super command just means whatever initialization protocol was there for the time step class, execute that. Okay, so our motion class now takes in the initial position and velocity. It initializes it using just the commands and in the time step by the super, using super. And then what do we want to do? We want to actually compute the trajectory. How would you do that? You would have time starting from 0. You would have a loop, like a while loop, going from 0 to tf, and while the time is less than the final time, what you would do, you would start at t is equal to 0. You would then use move, which is available in time step. We have inherited that. So you would say self dot move. Again, why do we use self? Because anytime you want to do something, you say self. It's sort of assigning that attribute to our instance. So this is just standard practice, right? You want to move a particle which is going to be created using this class, you have to use self. It's going to be moved using the function move, but it has that information has to be given to self. So you say self dot move and then it'll execute move. Now you need to go to the next time step. So you say t plus equals self dot dt, right? So that means go to the next time step. Now what our velocity is going to be, our vx is going to be 1, our vy is going to be 2 times t, remember? So then we say vy is 2 times t, and then you say self dot velocity is a tuple vx comma vy, because we know that the velocity is going to be given by this constant 1 and 2 times t. And if we have the velocity, right, and if we have the position, then your move function will do the rest. So now you go to the next time instant. You already have the position and the velocity. Move will again go to the next dt time instant. Then you'll update the time using t plus equals self dot dt. Again, you'll assign a new y component of velocity, x component is fixed, and then our velocity is vx comma vy, but we have to assign using self. That's why self dot velocity is vx comma vy. Again, you go to the next time step and you keep repeating. So that's great. And then let's say we actually create a motion object, which is an embodiment of the motion class. Once we create it, we just want to compute its trajectory. So you want to do the same operation. So what do we do? Then we say def underscore call self comma tf. Meaning, first I create an object of this motion class with this blueprint, and next thing I want to do is compute its trajectory. So when I want to just do this thing as soon as it's created, I have to do it using call. Anything, once you create an object of the class motion, the next time you call motion, you want it to just compute the trajectory, which means it has to be in the call block. So you say def double underscore call double underscore self comma tf, then you compute the trajectory, but you have to do it using self dot compute trajectory. Remember, using self dot is the standard practice here. So self dot compute of trajectory, and then you pass tf, the final time, and you just return the self dot position at the very end. So that's what this is. It does does take some time to get used to it, and we have some notes. So as we go along and see more examples and you sort of start using it operationally, you get a sense of it. But the key idea as a class is sort of a blueprint of creating these reproducible and interpretable structured data containers. And you can have all these operations. And you, whatever data container is there, in this case, it's a time step and you're moving through time. There are certain properties important which are called attributes, and they need to be assigned to an instance of this class. You do it using the self keyword. So you self dot whatever attribute property you want, self dot that property attribute is equal to that property attribute. You need to initialize things, right? You need an initial state. That's done using a constructor, and a constructor is a method, which is a fancy word for a function, and that's defined using the special keyword called init. So you have def double underscore init double underscore. You have to pass self as an argument to init, and whatever attributes, which are the properties you're interested in, have to be passed. And then you initialize it. Then you have whatever methods or functions you want to do operations of your interest. And after that, let's say once you initialize it, you want to do an operation. You have the call block. Call is a keyword, and that just means once I create an object which is an embodiment of my class, an actual thing, entity, the next time, once created, the next time you use it, you might just want to execute a certain operation to update certain attributes. And that is going to be done in the call block using the call keyword. So def underscore call double underscore, again pass self, do whatever operation you want. Again, you might have to use self. If it's a function in that is self dot that operation you want, and then return the quantity of interest, again using self dot. And child class is inherent from parent classes, meaning whatever was there in the parent class is accessible in the child class, and you initialize using the super command. So I hope this is clear. Let's run this. And now let's run the final code. So now you see our projectile is, what is the syntax here? Projectile is equal to motion into parenthesis, position is 0, 0, velocity is 1, 0. This means create an object of the class motion. Motion is a blueprint of reproducible and interpretable instructions to create this structured data container, which is again interpretable. And the syntax is class name, parenthesis, whatever parameters are, or which are basically properties called attributes required to initialize your class. So you pass this, it will initialize it. So that creates an object which is a physical embodiment of this class motion with the attributes position and velocity given to initialize it. Then next time what you want to do, you want to compute the trajectory, right? So then you say projectile underscore position underscore after underscore 2 seconds. I am using such specific syntax to keep things very clear. And then I say projectile, which is the name of an object of this class. Parenthesis, TF is 2 seconds. So now I'm using the name of the object, right? Which is an embodiment of this class, and saying TF is 2 seconds. When I use the name of that object and I pass TF, it is going to call the call method. I am like directly calling an object of that class. So whatever is inside the call method of this class will get executed. So what will get executed? Self.compute trajectory. And what does self.compute trajectory do? It runs through the time array, and at every time instant, it computes the physical law, or it moves forward in time. And that is done using the move function or method, which was defined in the time step parent class. So what should this do? It should create an object which is the embodiment of the class motion with the initial position 0, 0 and initial velocity 1, 0. And once this projectile object is created, we are going to call it, right, by the syntax name of object, which is projectile, and the input, which is final time is 2 seconds. It will get called, and then the commands in the call will get executed to compute the trajectory, which is, we are breaking it down, computing at every time instant, and you should get the position of the projectile after 2 seconds. And we had done this exercise using just raw code with automatic differentiation. So we are saying T less than TF. So our answer should be 0, something very close to 4. Let's see if that works out. So it's 2, 3.98. T was less than TF, so it should not be 4. So excellent. All of this is working. I have stressed on a lot of things in the class and tried to sort of keep talking over a lot of points. This is slightly tricky to understand, which is why I'm sort of trying to emphasize certain things. And you might actually have to get your hands dirty, write your own code to see how this works. But I hope this sort of different example has given you a flavor of how object-oriented programming and classes fit in the context of physics. And when I saw this the first time, these init and super and constructor and method and what else, parent class and child class and super, all of this sort of felt overwhelming. But sort of when you use it operationally for problems you're interested in, you'll see patterns and get familiarized with it. But the words are important. Like, think of a job interview. Think of talking to someone from computer science and not physics. They'll use these words, right? So it is important to have an understanding of these, which is why I've been trying to go slow and stress over these words. But also think of it operationally from a physics perspective. And think about relating it to this automatic differentiation and VMAP example. So I hope this has given you some flavor of what this is. I completely recognize and acknowledge that this is a crash course. It's very quick and you might not understand it, but I hope that you'll have this Jupyter notebook, you'll have me talking over these commands, and you can run this again, and you might run your own example and develop better intuition. But that is how I would motivate OOPs from physics perspective, right? So I hope all of this has helped, and I know this has been long. I've tried to really emphasize the basics because we will really need them later on. And the more you understand it, the easier it becomes. So I have seen some very, very nice videos. There aren't a lot of them, but there are some good videos on JAX. And I have seen them, but then they sort of don't necessarily break some of the Python things down. And if you're a physicist or an engineer, you might understand the physics part very fast and get stuck on inits and supers and like VMAPs, and then you might be like, what is happening? And then you try to run your own code and it doesn't work. And then things become a bottleneck, right? Which is why I'm trying to motivate things from the perspective of a physicist, so that any physicist or engineer watching this can sort of connect and understand these ideas. And when we actually go to the pin code, it should make things super fast, right? Because this shouldn't become a bottleneck, which is can become a bottleneck. At least it was personally for me. So that is another personal motivation of mine to have this long 1.5 hour video just emphasizing the very, very basics of Python and JAX in context of physics and pins. But I hope that this will really, really help you. Like, not even if you don't stick to this mini series, even if you don't do pin, even if you're just interested in like Python and computational physics and scientific computing, or even if you're just interested in Python, and maybe this gives you a very different perspective on how someone from a physics background thinks about this, that could be useful. So I hope this is valuable to everyone. And apologies for how long this was, but there's a very specific reason why this was very long. And I look forward to seeing you in the next class, which video lecture, which will be about the actual data cleaning, the data pipeline we use for pin. So we'll be actually looking at the data pre-processing, and that lecture should be pretty short. So this one and the PINN one is going to be heavy lifting. So be prepared for that heavy lifting later on, but I would suggest going through this step by step. Even if it takes you 4 hours on your end, it'll have payoffs in the long run. So thank you very much, and see you in the next video. Thank you. Bye. Peace.